afternoon. Uh, so, uh, I will be discussing about quantifying and mitigating the effect of snapshot intervals in the light cone epoch of reionization 21 centimeter signal. I have done this work with my supervisor, Professor Somnath Bharadwaj, in collaboration with Dr. Rajesh Mathur. So, light cone effect is the very fact that our view of the universe is restricted to a backward light cone, and that can be written using this formula. That can be written using this formula R equal to C eta naught minus eta, where eta naught is the present epoch and eta is the epoch when the source emitted light. From this light cone diagram, we can see that the observer is at here at the vertex, and a physical volume of the universe is correspond to also a temporal interval. And we see along this along the line of sight of the which is the line light follows, and for a particular wavelength, due to the expansion of the universe along the line of sight, the redshift changes. So at the observer, redshift is 0, and along the line of sight, it changes. Now, this light cone effect is significant during the epoch of reionization, as the mean neutral hydrogen fraction changes rapidly during this epoch. For this work, I have chosen this region between redshift 7 to 8, where the mean neutral fraction changes from 0.16 to 0.49. So this box is 286.7 megaparsec cube, and this is the line of sight. So we can see that neutral fraction statistical properties H1 fluctuation changes substantially in this redshift range. So we should consider light cone effect. Now, this is the simulation pipeline we use. This is a semi-numerical simulation which consists of mainly 3 steps. In the first step, we simulate the dark matter distribution using a particle mesh n-body algorithm. In the second step, we find the halo positions and halo mass using friends of friend algorithm, which is the slowest step also. And in the third step, we calculate, we use those halo field and dark matter field to finally calculate the reionization map using reion Vibhav. Now, having those reionization cube, we can simulate light cone cube by taking slices from those reionization box. So we have reionization simulation at different epochs, and then we take slices from them and fill the light cone box. So from the first coeval snapshot, we take particles from the first slice to fill the first slice of light cone box. From the second snapshot, we take particles from the second slice to fill the second slice of the light cone box, and so on. So now in the light cone box along the line of sight, we have information for different epochs. This is a typical, this is a coeval box and the light cone box for for our simulation, where we can see in the light cone box along the line of sight, which is the horizontal axis, we see the evolution of the bubble sizes. So in the more past epoch, which is the right side, we see bubbles are smaller compared to the coeval snapshot, whereas in the more recent epoch, we see bubbles are bigger compared to the coeval snapshot. So now the issue is the choice of snapshot intervals or the number of coeval snapshot for a particular light cone is ad hoc, and we want to quantify, also want to mitigate the error in the simulated light cones due to finite number of coeval snapshot used. For this work, I have started with 26 snapshots within this redshift range from 7 to 7.9. Then I create a light cone for 26 Quavel snapshots. I then removed one snapshot consecutively. Now I have 13 snapshots. I create the light cone for that. Similarly, again I do the same thing and create a light cone with 7 snapshots and so on. Now we have light cones which are of same size. Each light cone is 286.7 megaparsec cube and span the same redshift range, but they created using different number of snapshots. So let us see what. So this is the power spectrum. We can see the overall power spectrum decreases as we decrease the number of snapshots. Now, as Kanan discussed yesterday, power spectrum is not a good metric to quantify this error. The appropriate metric should be maps, because power spectrum assumes homogeneity, statistical homogeneity, and imposes periodicity in the signal, which have been studied by Mondol et al. Also. So we will use maps to quantify the error. Now these are maps for our light cone with 26 Quavel snapshots. We can see the maps signal is high, peak around nu1 equal to nu2, and as we increase the delta nu, the signal falls rapidly. Okay, so now this is the maps for different light cone simulations. So for 26 light cone simulation with 26 snapshots, 13, 7, 4, and 2. By just looking at maps, we cannot make out much. We cannot see much difference. However, when we plot the differences, so we take 26 snapshot light cone as the standard and calculate differences for other light cones. Now we can see there are different, nice patterns are appearing. So as we decrease the number of Quavel snapshot, the difference increases, and this kind of pattern, they are basically discontinuities, and these discontinuities are arising at the stitching boundaries of Quavel snapshot, which can be better seen if we plot only the diagonal element of maps, which is CL nu. We can see as we decrease the number of Quavel snapshot, this step-like behavior in the maps, in the diagonal element of maps is observed. So this is because at the stitching boundaries, when we use a small number of Quavel snapshot, the changes in neutral hydrogen fraction, average neutral hydrogen fraction, is abrupt. Whereas if we use sufficiently large amount of Quavel snapshot, the changes are smooth. Here I am showing the differences for the error in the diagonal element of maps, considering the light cone with 26 snapshot as standard. So this top row, I am taking it the standard light cone, and then calculating error for other rows. Then we can see as we decrease the number of snapshot, error increases, which is obvious. We expect also. Okay. So now what we learned that one should use significantly large number of Quavel snapshot to reduce the error. But that is quite computationally expensive in terms of RAM, storage, and processing power and time. Because generating those snapshots takes time and memory. So let us introduce a new technique to mitigate the error. So the idea is we will generate in between Quavel snapshots using the available snapshots only. We won't generate it from scratch. We will use the available snapshot which we have and generate in between snapshots. So here we skip the first and second step of reionization simulation, that is basically generating dark matter field and finding the halo, which is the most time-taking step. These two steps takes around 97.5% of the total time. So we skip them and directly we will do the third step, that is finding reionization map. Now how we can do that? We need these fields, right? We need dark matter field and halo field. So let's say we want to generate we want to generate a certain number of in-between snapshot, and we have these snapshots available. By available, I mean that we generate this from scratch, a lesser number of snapshot, but we now try to increase the number of snapshot by generating in-between snapshots. Okay, so the idea is we take the dark matter distribution and halo catalog for the available snapshots, and then we will grid them. We grid the dark matter field and the halo field, and then at any in-between redshift where we want to generate a new snapshot, we just take the weighted average of the dark matter field for the two side available boxes. Okay, so let's say Zi and Zi plus 1 are the available box, and in between I want to generate a snapshot. Then I will take the dark matter field and the halo field from the two side box, and here we consider a simplest simplest weight for the simplest weight, which is the redshift interval. And the underlying assumption is we consider a linear cosmological evolution. Now, finally, after doing this, we have increased the number of snapshots. So we had these available snapshots. Now we have these in-between snapshots also created. So this process increased the number of snapshots by this amount. Okay, now let us see the plot again. Now here the red line is after applying this technique. So we can see for 13, 7 and 4, for lesser number of Quevel box also, after applying this technique, we are able to reduce the error significantly, and the error reduces less than 1% for most of the cases. For 2 snapshots, however, the error is within 2% limit. So for just give you some number, this table shows the average percentage error. So for this fluctuation, I have taken average. So one can see the how much we can reduce the error. So in most of the cases, the error is within 1%. For two snapshot, the error is within 2%. Okay. Now we use the same technique we have 26 snapshots. We use the same technique to generate 1, 3 and 7 in between snapshots, which allow us to simulate a light cone using 50, 100 and 200 Quevel box respectively. By doing this, we can see if we want, if someone want less than 4% error in the light cone simulation, then they need to take 50 snapshots. If they want less than 2% error, they should take 100 snapshots. If they want less than 1.5% error, they should take 200 snapshots. Okay. So this method is very effective to reduce the error in the simulated light cones. Just to give you some number, in a computer at IIT Kharagpur. So if we wanted to generate this 200 snapshot light cone from scratch, it would take more than 4 months to generate 175 in between snapshots. Okay. Now assuming so by this method, this in between snapshot generation would take less than 2 days and also less memory. So finally, the error can be quantified if we plot the average percentage error with number of Quevel snapshots, and we see they are nicely following a power law. We fitted the power law and find an exponent 1, which says that average percentage error is inversely proportional to number of CB used. So for our work, if we put the number of CB in this formula, we will get what is the average percentage error. In contrast, the power spectrum also give the same result, but for small scales. At the large scale, however, we know that light cone effect is important, and in power spectrum, we know that at the large scale, so power spectrum gives biased result. That is why these two lines are not following the fit. So this is the summary. The error in the light cone simulation inversely proportional to the number of Quevel snapshot used. The error can be calculated using this formula, and the error can be reduced to a great extent assuming a linear cosmological evolution to generate in between snapshots. This technique can be used to fasten the light cone simulation pipeline, which is highly effective to generate multiple realization and doing statistics. Thank you.
Thank you, Suman. Questions, Prakash? Yeah, so you use linear interpolation between the two redshifts.
Yes.
If you use 3 snapshot and use the cubical one or
Yes.
quadratic, would the error would reduce?
So we could have done that, but we haven't checked that. So because for the only taking, I mean the linear interpolation, we get we have reduced the error sufficiently. So we haven't checked that, but I will definitely check if it reduced more.
The other thing is, do you also interpolate the halo catalog?
Yes, both the halo catalog.
If you form a source in between the zi and zi plus 1, what will happen now?
Yeah, we're missing basically that information, but still it is giving a good agreement.
Yeah, I mean, the other thing is whether your 26 snapshot, is it converge? That how do we know that? The 26 snapshot.
We don't know. We start with 26 snapshots, and and take it. I mean, we could have started with 50 snapshots also.
I mean, that number, that 26 or 50, would come from the physics, that how fast the ionization front is propagating, right?
Yes.
Or how quickly the sources are forming.
Yes.
So that should be based on physics rather than our limitation, no?
Yes, I will.
Thanks.
Nice work, Suman. Just I wanted to know that your exercise, whatever results you have shown, is it for a particular rate shift or stage of reionization? Let's say you are doing the same exercise for the end of reionization or the beginning of reionization. Does your result change?
Yeah, so that I have to check. So this is particularly for this redshift interval. So if we so
50% reionization.
Yes, the fiducial model, which gives 50% reionization at redshift 8. So the result could have changed a little bit if we consider different reionization history, and also
particularly when reionization proceeds very fast at the end of reionization.
Yes. So that could change the result, but I have done this for only this interval. Yeah.
Thank you.
Yeah, very nice talk. So maybe I didn't understand this, but the interpolated boxes are just the densities and halo catalogs, not the neutral hydrogen density, right?
No.
So the neutral hydrogen density in each of the interpolated boxes, is that obtained using some excursion set type stuff, or
no? They again, I use Ria and Yuga to do that. I mean,
yeah, I guess right. So is but what I guess. What sets in Ria and maybe I need this is a Ria and Yuga question now, but yeah. What sets the Q value as a function of
excursion set formalism of fluid?
Correct, but then excursion set formalism doesn't know what Q to assign at a given Z.
What? Sorry?
At a given redshift, excursion set wouldn't know what Q to assign, right? What brightness to set for your halos.
Yeah, so basically the interpolated halo catalog may not be the exact halo catalog. These are maybe
okay, so you're also interpolating the halo brightness.
Yes.
Oh, I see. Okay, I didn't understand that. Okay, thank you.
Other questions, comments?
Nice work, Suman. So what I wonder is that how will you so this you have done without the effect of peculiar velocities, right?
No, this is with effect
peculiar velocities.
Yeah, with considering peculiar velocities.
How do you exactly incorporate that?
So basically we also in the n-body simulation we store the position as well as the frequency of the particles. The frequency are calculated using peculiar velocity, and those frequencies are then used in the final light cone simulation. So here you might ask, in the in between snapshot, how we get those frequency informations. So for the in between snapshot, we take the frequency information and particle position information from the previous available box. Okay. So if we want to know what is the redshift space distortion here, then we have to do n-body simulation for this redshift from scratch, and I am not doing that.
Okay. Not sure if I understood it, but
Yeah. So I am taking the particle positions and the frequency. The redshift is basically frequency information and particle position information from the previous snapshot and using that in this snapshot. But now the halo catalog is different, which is interpolated. The dark matter distribution in the grid also interpolated, but the particle position they are taking directly from there. We cannot interpolate them. In grid we can interpolate, but positions we leave all there.
You do interpolation on dark matter simulation, but if you do the same thing on the 21 centimeter maps, directly on the 21 centimeter maps, have you done that?
I have done. Yeah.
Okay.
Okay, if there are no more questions, let's thank